And welcome back. We are discussing section 6.3, Improper Integrals. So this is ostensibly the part of the video where we get to the second learning objective, but we're really kind of going with most of these. So we'll just check boxes everywhere. Everybody's checking boxes. Box, box, box. We're going to tackle everything. But we got to get to the right slide first, so let's do that. First thing to address is kind of a non sequitur, but it comes up so much in some of the integral evaluations that it's worth kind of looking at this special case. So we've talked about a couple of special limits earlier on in chapter 1, but one of the most interesting ones that we haven't addressed is what happens when you combine power functions, or polynomials really in general, and multiplied to some sort of exponential decay function. So this is sort of a competition, because if n goes to infinity, then this thing kind of wants to go to positive infinity, and this thing kind of wants to go to 0, and then you say, who wins? I don't know. Actually, we do know the exponential function always wins. So it doesn't really matter how big this exponent is. It could be n to the 15th power and e to the negative 0.0001 n. Eventually this e to the negative business will carry over. And just by way of illustrating this key fact, because this limit comes up a few times, visually we could see, just for a specific case, would be x cubed and e to the negative x. So in this case, p was 3. That's our exponent on this polynomial. I guess k or a is 1 in this case, but regardless, no matter what you get here, if you've got a negative exponent on e and some polynomial getting multiplied to it, it may in the short run have this kind of spiky growth, but it's going to level off towards 0. These functions actually are sometimes called surge functions. Then you can model some really cool stuff like changes in stock market price or concentration of drugs in the short run, because there's an initial kind of bump up, but then it settles back to its equilibrium value afterwards. But regardless, mathematically, the thing we're going after is that you multiply a polynomial times some exponential decay, and as x gets bigger and bigger, this is going to go to 0. One thing worth noting, just again mathematically, is that this is the same thing as writing e to the x in the bottom. Just that negative exponent drops it down. So just because you see a fraction, don't assume that this doesn't apply. These are the same thing, just without the negative exponent in there. Okay, so if that comes up, great, now we've got a strategy. So the last example we're going to try to tackle still pertains to mostly the type of integral we're most likely to see. So the one that is most common in almost any application is where there's a finite lower limit and an infinite upper limit. So going from 0 to infinity, or from 4 to infinity or something. But it is still possible that we might run into the case where we're curious about both directions, where you can go to negative infinity on the left and positive infinity on the right. And we need to figure out how to tackle that. So the way that, and maybe just to illustrate the conundrum, if you've got infinities on both of these, the way this should work is you just let one of these things be, call it some letter, some variable, and then let limit as that goes to, say, negative infinity or positive infinity. But we'd have two different limits here. So the standard way to approach this is basically to pick an intermediate spot. Well, between infinity and negative infinity are all real numbers, so you could pick anything for this. It literally does not matter, any real number. So c is some value that you get to choose, and then basically you're going to calculate the two integrals like the one that we did in the previous video. So you have some finite lower limit and an infinite upper limit, or vice versa. It's the same deal, but that means you only have one limit for this guy and one limit for this guy, and it'll be easier to manage. Okay, so we'll try out an example. So find value, as you might have predicted, it's going from negative infinity to infinity, and then we get some interesting fraction. So we either are supposed to find this value or state that it diverges. Okay, so we're going to break this up per the helpful suggestion we got before. We get to pick the c value. In this case, c is equals 0 would be kind of nice, just because 0 is such a great choice in general. But again, I should make sure it's clear. This choice for c does not matter at all. It will not affect our answer. And when we get to the actual computation, I'll try to call out why that's true. But in the meantime, we've got two different integrals that we're supposed to compute, and that's, you know, never trivial. But these don't fit the general like power rule kind of models. So what I will notice is that if we looked at x to the fourth by itself, its derivative would be x cubed, and that's part of this integrand. And that's a great part of the substitution decision-making process, that if we picked the substitution with the denominator being the thing we substitute, then we would end up with something whose derivative would actually help us clean up the numerator too. And I guess two birds with one stone here, given that we are looking at the exact same integrands between these two, the only difference is where they go between, we can use that same substitution twice. So I realize this is kind of a mess because there's a lot going on here, but just remember we have replaced, here is u being replaced in those spots, and then we've got the substitution derivative piece helping us replace dx with this whole monstrosity here. But that's going to do us a favor because you have x cubed in the denominator and in the numerator, and so those will cancel, which is delightful because then you'll be left with two integrands that are much nicer to compute. I want to point out I'm doing something a little unorthodox with these limits. X equals 0 is pretty standard because I want to remind myself that it's not actually u equal to 0. It's this previous variable, this x thing. This is the non-standard thing though, so writing x going to negative infinity, there's this complication when we do both substitution and this improper integral thing that's kind of unwieldy. So I'm not using an equal sign because I'm not going to have a real number that's equal to negative infinity. But I can sort of say, look, we're going to let x go to negative infinity and remind myself that it's not actually the u values necessarily that are getting smaller and smaller. So that'll go away. That's just a convention I've adopted for my own sanity. So what we're really left with, though, after all this integral tidying up, is a factor of a quarter and then 1 over u inside the integral. But we're pretty good at managing that. I will be careful with the absolute values this time because we actually do have some negative numbers that could go in here. So little m here is what we're using for our limit, our index of the limit. So little m almost certainly is a negative number because 0 is the highest we're going to go, and we're going to try to explore what happens as plugging in an m gives us a smaller and smaller value for this. On the other side of it, I'm using capital M because they're going to different things. I need to label them differently. But it's the same deal. We're going from 0 to that capital M, and we'll see what happens when we plug in M and let capital M and let it get bigger and bigger. So here's a huge mess, but we'll clean it up. We'll put in 0, we'll put in little m, and then over here we're going to add that result to big M going in and 0 going in. And so I just kind of want to take a moment with what we've got here. So this would be the result of plugging in 0, because it would be natural log of 0 plus 1, which is 0. This is also that same thing on the other side. And just to kind of point out, these are the results of our, these are from our choice of C. And sure, we had to integrate and stuff to get there, but the only thing that can change between these would be based on the value of C that we picked. And no matter what, they happen to be 0 in this case, but sometimes they could be like 5. So this is minus 5, but we'd also have plus 5. So the value of C doesn't matter at all because these two integrals are always going to have those values cancel each other out. It's kind of like in that constant of integration where you have the plus capital C thing after you do some indefinite integral. And then when you go to definite integration, the plus C doesn't matter anymore because you would be subtracting it in all cases. In any event, the moral is the choice of that C didn't actually matter in this case. It didn't affect how this infinite integral situation is playing out. But these actual little integral thingy, or these little limit guys are going to affect things. So now we have to think, okay, if little m goes to negative infinity, that's going to be some really huge negative number raised to the 4th power, and the 4th power is going to make that positive. Adding 1, fine, you won't notice that much, but then you're going to take the natural log of some really big number. And the further negative you go, the more pronounced that problem becomes. It would be an even bigger number raised to an even to a 4th power, which would be yet a bigger positive number. Add 1, take its natural log. These things continue to get bigger and bigger and bigger. So this piece right here is going to keep going to infinity, And this is the mirror situation. Now plugging in a big positive number, raising it to the fourth, that's still positive, plus 1, and so we'd be all done. Just as a note, as soon as you notice that one of these limits hits infinity, it's game over. We aren't going to get canceling infinity things happening here. We're going to make sure that as soon as one of these things doesn't have a limit that exists in some fashion or another, then it's game over. We're done looking. So I checked this second thing just to illustrate that its limit is also infinity, but doesn't change our answer. So just in words, m to the fourth plus 1 in either of these cases is going to approach infinity, so will the natural log of that quantity. So we're going to get that the integral diverges. So that is it for improper integrals as far as we're going to tackle them anyway. We'll see you in the next section.